All right, our next speaker is Hassane Trigui from R&D Center Aramco. The title of the presentation is Underwater Robots for Shallow Water Pipelines Inspection and Monitoring.
Good afternoon, everyone. Thanks to all for inviting me, to Mohammed Shihab, Dr. Mohammed Shihab, and Professor Eric for giving me the chance to speak today about what we do in our research center in Aramco. So, all right. So my name is Hassane Trigui. I graduated from KAUST in 2012, and then joined Aramco after that as a master graduate. And I worked with the Research and Development Center right now for about 10 years. First of all, before I jump into what we do for underwater operations and research, I would like to give a brief about our team. I trust everyone knows Aramco. It's probably the largest oil and gas producer company in the world. They have a capacity of 12.5 million barrels production per day, probably even more than that. There are probably what others don't know is the amount of infrastructure and network that exists in Aramco. There are thousands of storage and custody transfer tanks, probably also tens of thousands of pipelines distributed across the company and within the facilities, and also like hundreds of thousands of equipment and instruments that need to operate every day, right? And you need to make sure that they are in well conditions and they're maintained and inspected periodically. And that's what we call a network in Aramco. Network is not like what we know in the academic, social networks or like any other of networks. But here, like the pipelines and the pipings are our edges, and the equipments and the instruments or the tanks are our node. And our team Intelligent Systems Lab is part of the Oil and Gas Network Integrity. This is where our mandate is to develop technologies that make sure that the integrity of these infrastructure is well maintained. I will give a brief about all of these technologies that we developed, just quickly, one slide per each, so that you get the flavor of what we're doing in our lab. But before that, this is our lab here. It's located in KAUST. It's between Seymour and it's after Seymour, basically, between Seymour and Dow. We moved recently 2 years ago. So this is the Intelligent Systems Lab. We have a design studio where we develop our mechanical and electrical and software as well programs. And then we have a prototyping lab where we prototype our ideas, and then the testing facility that has multiple equipment such as drone cage, like many of the instruments and equipments that we have in the field in order to test our developed technologies or prototypes on them. Okay, sorry. Okay, so this is the first project that we started with. We were actually 7 graduates of KAUST during that time in 2012. We started with this project. It's called Saudi Aramco Inspection Robot. It's basically a crawler, a magnetic roller that attaches to steel surfaces, pipes and tanks, and performs what's called ultrasonic thickness measurement and also visual inspection. So, metal gets corroded, and that's a problem in oil and gas. So you have to monitor this and inspect this corrosion rate and make sure that it doesn't go below a certain rate. In many cases, we found that you start with 12 millimeter or something, and after some time you end up with 2 millimeters. So you have to make sure that the corrosion rate is controlled, and this can lead into like leakage or cracks. And this is a device that we developed in-house. Sorry, the video was so quick. I should have spoken quicker. But it's probably the first, I believe it's the first wireless UT inspection robot that was delivered to the market. Probably right now there are more, but it was the first compact wireless, and also it has high agility, as you saw probably in the video, on elbows, which is a very added value to this robot compared to what's available in the market. And even we believe until now, like it's superior in terms of the agility, in terms of the in terms of the agility and flexibility on elbows and curves structures. The second robot that we developed was called robot dust mitigation. It's similar to Nomad. It has some other features. So it uses dry cleaning to remove the dust depositions on the solar panels. It's automated and uses special brush. It's called silicon rubber foam brush. And this is what you can see the difference. If you clean daily, there is like a clear difference between, there is clear difference between a clear difference between if you clean daily or monthly or weekly. If you clean daily, and you will get like the best performance, and you will avoid having any sand deposits, stick on the solar panel surface. This is a third project that we also developed. It's for it's for tank calibration. Custody transfer tanks, these are tanks where Aramco transfer the custody of the oil, and they have to be well calibrated periodically, like every few years, because these tanks, by the hydrostatic pressure, they expand by higher rate. And if you don't capture this expansion, basically we're giving free oil to the customers, which we want to capture. And this is automating an API that is followed by Aramco and by the oil customers, which is called the sorry, I forgot the name of the API, but basically it uses trolleys, and it uses like vehicles in order to estimate how much expansion or how much deviation of the wall of the tank from its bases. So this video shows a vehicle at the bottom, or a station at the bottom. It shoots a laser to the top, and then a vehicle that climbs all the way to the top, and there is like a let's say a ruler, but it's like a laser photodiode composed of laser photodiodes. And it detects where the laser hits, and then by that we can estimate the deviation or the bulging of each of the strips of the tank walls. But when we perform this on multiple locations, we can project the 3D model of the tank, as you can see here, and then we can estimate the wall profile using that. So this is a followed API that is being used, but we developed a robot to automate it. Currently, it's manual. You have an operator that climbs the wall and the wall of the tank, and then pulls a trolley, and then there is a person at the bottom. They look at where the like they look at where they see the roller, and it's very slow process, and also like expensive process. So by automating it, we are able to reduce the time and also the cost, and also increase the accuracy because of the nature of these photodiodes. This is a fourth project that we are currently, it's actually an ongoing project in collaboration with RESC. Fadl Abdulatif is doing PhD on this project. So it's called Falcon Scan. It's a flying aircraft, and that carries a launchable crawler. to perform NDT scans. It's somehow similar to the first project, SIRE, Saudi Aramco Inspection Robot, but it's basically a drone that is hybrid. It carries a crawler. Sorry, I don't have a video because it's still an ongoing project. It carries a small crawler, like a small SIRE, and once it reaches to the top of the pipe, or actually it can attach to multiple angles of the pipe from the top or from the side or even from the bottom, because I'm not sure if there is some. Yeah, because this arm, this is where they attach, this is where the magnets are, and this arm can be rotated so that you can attach to multiple orientations. And it releases a crawler. This is the place of the crawler where it is deployed. It performs ultrasonic thickness measurement as well. Also has camera, and then once the data is collected, it is retrieved, and then the drone would fly back. As I mentioned, this is still an ongoing project. I don't have further details on it, but it's clear. All right, Swimmer. This is a shallow water inspection robot, inspection and monitoring robot. This is actually also developed in our facility between 2017 and 2018. Actually, no, maybe 15 and 18. I will give, before I give more details about it, I would like to share the challenge. So, and this is something that I did not share with you, but it's, before we start any project, we receive challenges from the field. So we cannot just do any, academic projects, for the sake of research. Like any project has to be research, like business-driven project, and we need to have a proponent from the field. So we received this from the Marine Department in Aramco, and you can see the amount of the these are the structures that we have in the underwater underwaters. There are like these platforms and also structures of these platforms, as well as pipelines that go from the onshore all the way to the deep waters. These pipelines, they leak, they corrode, as well as like similar to the pipelines that exist in the land, and that's why we need to monitor them and inspect them periodically. This is an example of a pipeline. So pipelines usually are split in 12 meters, and they're welded together. So underwater, there is the concrete weight code so that they are fixed on the seabed and they're not floating. However, the weld sections, these weld sections are they're the most like the weakest points in the pipeline, because usually that's where they leak, and they have to be inspected every 5 years. Yeah. So what do you expect? Like, which one is more difficult, like inspecting the pipelines in deep water or in shallow waters? I think intuitively, like deep waters is more difficult. However, like during the due to the regulations and policies in Aramco, the shallow waters regulations are more difficult and more expensive as well. I will show the reasons here. So for deep waters, what we call deep waters in Aramco, because most of the operations in Aramco are in the Gulf region, the Gulf, Arabian Gulf, and most of the operations are below 65 meters. So in global waters, that's still shallow waters, but in Aramco terms, deep waters go beyond 10 meters, like deeper than 10 meters is called deep waters, and less than that it's shallow waters. So in deep waters, there is like, imagine this is a pipeline that goes all the way from the shore all the way to the offshore and then to the deep waters. So in deep waters, they use driving support vessels, they use divers, as well as world-class ROVs. They carry most of the sensors and equipments that are needed in order to perform the operation successfully. And these vessels, they have dynamic positioning, and the divers, like in Aramco, scuba diving is not accepted there has to be like a tether connected all the time to the diver, and that's why dynamic positioning on the vessels must be on, so that you make sure that the vessel is not moving. And in shallow waters, the DSVs don't like the dynamic positioning doesn't work less than 10 meters. So they use other techniques in order to make sure that the boat is not moving and stationary, and they perform like a 4-point anchor, and that's like slower and more expensive. And also, like, the world-class ROVs cannot operate in shallow water, so they have to use divers, they have to use DSVs, but it's more challenging and slower as in terms they have to anchor to the ground. In even shallower than that, less than 5 meters, they use Zodiacs, and there has to be also a DSV on standby because they use divers, and there has to be like a vessel that is close by within 20 meters in case of an emergency that occurs to the diver. The DSV has to be available. And in Aramco, less than 10 meters, we have 25% of our pipelines in less than 10 meters, which is like a huge. And since there are no ROVs, at least during that time, I'm not sure right now, I didn't do like my due diligence properly, but during that time, there were no ROVs that perform inspection tasks for shallow waters that are less than 10 meters or less than 5 meters. So we took, and this is just summarizing, it's the shallow water and the inspection in shallow waters is actually 4 times slower and 2 times more expensive than in deep waters, and that's our business case. And also the other business case is safety of divers. This is actually real footage that we collected from our robot. This is called a yellow-lipped sea snake. They have a neurotoxic venom that's 10 times stronger than rattlesnakes, and this is in shallow water. So that's very dangerous, right? Swimmer, and that's how we came up with this idea and started this project. Is we developed a robotic system with integrated inspection technologies that can be operated in shallow waters to reduce inspection costs. The functionalities and features that we wanted to have in this robot is to be small size, deployable from a Zodiac, because Zodiacs are the only possible ways of accessing these shallow waters. Have hybrid mobility for shallow water navigation. As you can see here, there is the tracks and also the thrusters. Also have the ability to clean local marine growth, as well as perform the inspection. In order to reach to the metal, to the bare metal, we need to perform the cleaning so that we can measure the thickness of the pipe. We started from concept sketches all the way to the robot that you can see in here. And one of the features that we wanted to make sure that exists in our robot is modularity, because there are multiple functions, and you have only like one platform. So we wanted to make sure that all the functions that we needed can be integrated, assembled, and disassembled from the main platform. You can see here there are there is the cleaning brush and the cleaning nozzle, and there is also the robotic arm that carries the end effector that carries the sensors. There is also the tracks. So by having our platform to be modular, we can build as many configurations that we want. We have here 2 configurations. This is the cleaning robot. It has the cleaning nozzle in here, and this is the inspection robot that has the robotic arm with the end effector and the sensors on top of them. This is the I'm going to show some like few models in here just to show the parts. So this is the electronic hull in the middle, and the like it's waterproof, rated I believe for 25-30 meters. However, our business case was built on 10 meters only. The battery pod is waterproof as well. It has 8 cells. So we wanted to make sure also that it is self-contained in terms of the power. The power is is given through a battery that is like integrated on board, and it's not given through a cable. So that in the future, if we manage to find a solution for wireless communication, this is still, you know, something that we can get rid of the cable basically. The lifetime of the battery is between 2.5 hours and 3 hours. These are flotations that were added because for different functions, you will need sometimes like negative buoyancy or positive buoyancy. So we had this also a flotation block as a modular system or block that we can integrate or remove. And this is also the chassis. We made sure that it's anodized aluminum so that it's corrosion resistant due to the environment that we see in the sea. The buoyancy is designed to be passively stable. We made sure that the center of mass is in the middle, and the weight and the buoyancy, like both of them are on the same line, so that we don't have any instability. The locomotion, we have two systems for locomotion. The two crawling tracks from Minitrack. They have 45 kilo of payload, and their clutch as well. There are also 4 thrusters in order to move up and down and forward and backward, and also rotate in position. They have 6 kilograms of thrust force, and they're oil compensated. The robotic arm, which carries these sensors, that's 3 degrees of freedom. We have the shoulder, the elbow, and the wrist. It's actually, during that time, there were no electric robotic arms for ROVs, and I'm not sure if I can claim that it's the first electric robotic arm. But yeah, it's not like what you see in deep water or in world-class ROVs, pneumatic arms. And this is we wanted to procure actually this robotic arm, but we couldn't find it in the market, so we designed it ourselves. So the end effector carries the thickness gauge sensor, which is an ultrasonic thickness UT sensor. It measures the wall thickness of the metal pipe. The voltage gauge, this is cathodic protection. So so these pipes, because they corrode, so there is a technique that if you provide voltage or current to these pipes, it basically stops or slows the corrosion. And there are anodes and cathodes. Sorry, there are anodes that are attached to these pipes to provide this current, this small amount of current, so that it stops the corrosion. So by measuring the voltage on these pipes, we can know basically like if the anode is depleted, it needs replacement or not. There is also a camera on board. There are magnets and also 2 passive degrees of freedom, so that it attaches to different curvatures and has flexibility basically to attach, because the UT sensor has to be perfectly attached to the pipe. For visualization, we have here a motorized camera. Sorry, I always lose the track. So it's 2 degrees of freedom. We have 180 degrees pan motor and 130 degrees tilt motor. It's an HD camera. We have also 2 flashlights for low visibility or low light operations. These are the navigation sensors. So we have the 2D sonar in the front. It gives like in case of bad visibility, it gives us like better hint where is the location of the pipe or the area that we want to inspect or detect any obstacles in front of us. The inertial measurement unit as well is also integrated inside the electronic board. The altimeter, it measures the altitude. There is also a pressure sensor inside the electronic board, which outside. I'm sorry, it's outside, but probably it's not here. It measures the pressure so that we know the depth of the water column. The end effector again. Yeah, this is the ultrasonic probe. This is the arm camera. It was placed here so that we make sure that the ultrasonic probe is perfectly attached to the pipe. The 4 cathodic protection probes and also 2 magnets in here. 4 magnets. I'm sorry, 4 magnets in here. Also, one element here is the robotic arm can reach to multiple locations, multiple orientations from the top, from the bottom, even from the other side, and it can extend up to 1 meter. And it was built such that it's neutrally buoyant, so that it doesn't have any effect on the or instability on the robot. This is the electrical system. Has basically 6 printed circuit boards that carry two carry microcontrollers, one for motion control, one for data acquisition, and one to regulate low power, and also one to regulate high powers, and one to control the thrusters, and the other one to control the PCB and other equipment, the tracks, sorry, to control the tracks. Camera here, the IMU is here. Cooling fan is also provided in here, and we're using these MCBH connectors. There is also a motherboard on the bottom that connects these all together, connects these boards all together with all the sensors and actuators from the outside world. I'm not going to go into details. This is basically a chart that shows the software and the electrical architecture of the robot. So controlling swimmer. So what we developed is, so this is the umbilical cord that connects and provides the communications, only provides the communication to the robot. And there is a router that is mounted in here, and we connect wirelessly to this router. We're using the NVIDIA Shield to control it. And also we're using FPV goggle to show video, to see the video, because under sunlight and hot conditions and in Saudi Aramco, there is like a glare on the screen, and you wouldn't be able to see much. So and also you wouldn't be able to see the robot as well. So we were using these goggles to have a better visibility. Yeah, this shows the control of the robot. This is the what we see in the FPV. So we have here the thruster status, the depth, the altitude, the percentage of the power of the battery, where's the front camera oriented, the sonar data. Here is UT and CP measurements. Here is the location of the I believe this is magnetometer or like yeah, it shows the orientation. Here we have multiple functions to control. So if you are in a robotic arm status, you can have like fast functions, whether you want to reset the arm, extend, fully extend or fold or retract in a position where this is, I believe this is the retract position where it's ready to take a measurement. So you can have these quick configurations. There are multiple configurations. For sake of time, I'm not going to show all of them. This is a video of swimmer. This picture actually was taken here in KAUST. So it was tested in Seymour. They were generous to lend us or to give us one of their tanks, test our swimmer, and also tested in the Red Sea, also in the Gulf. We'll see some footage here combined testing. Or actually, most of the footage here is in the Gulf. You can see a Zodiac. It's 25 kilos. Or 30 kilos, one person can throw it. You can see here the cable and the two configurations. This is the green cable that shoots the water. It's cavitation water. We're using cavitation water to clean the marine growth. And this is the extended arm of the inspection robot. We're using divers here to take the footage. Here we're using the crawlers. This is the snake taken from our camera. These are the pipelines. So they're like at the welds here, they're exposed, and this is where we have to perform the cleaning. Some welds are clean and some welds are dirty. This is a weld like a covered weld that we have to clean before we reach to the bare metal. And here it shows the span underneath the pipe where sometimes we have to take measurements at the bottom. This is the Gavi plaster, shoots cavitation water jet, which is a mixture of water and bubbles. The compressor is on the top of the Zodiac. and it shoots water. It's very effective in cleaning like local barnacles and local marine growth. And after that, after we reach to the bare metal, we deploy the robotic arm to take our measurements. So here it has to be in proper contact in order for the UT and cathodic protection. All right. I'm about to finish, sorry. Okay, this is just a lab view model. I believe that's it. All right. So there are 3 modes of operation. We use Zodiac to throw the robots, inspection and cleaning robots on the pipe. That's mainly above 3 meters. When we reach to areas that are less than 3 meters, we made up a configuration of having an autonomous surface vehicle that follows the underwater ROV and tracks it. And basically, we can relay the signal between the operator in here, ROV operator, to the service to the ASV, and then the ASV will have the tether connected directly to swimmer. And this is because there is like a lot of area that are very shallow in the Gulf region, and this is very important configuration. This shows the ASV tracking that we developed. So this is an off-the-shelf boat that we acquired, but we modified it. We added a long-range antenna and then acoustic tracker, and then sorry, this was tested at night. Was actually a collaboration between our team and Risk Lab to develop like a controller that tracks the ROV underwater. And this is a successful tracking, but I'm sorry, I don't have evidence for that. That's it. So the awards, swimmer was received the CEO Excellence Award back in 2017 for its achievements, and also received more than 10 granted patents. It's currently licensed and being commercialized by RPDC, Research and Product Development Company, which is a Saudi company. Yeah, I'd like to acknowledge all the team members that work on these projects, RPDC commercialization team, Risk Lab, and also the organizers. Thanks all for this opportunity.